Hello, everyone. I wanted to start out this video going over Chapter 1, Section 1.3. We're going to be continuing on to evaluate a screening test using the same data set that we've been using throughout the chapter. So we're creating this data frame, once again, that has patients with the disease and whether or not the patients tested positive or negative for that disease. So we create our data set. And once again, we're going to re-level the factors such that they're not alphabetized, but we're going to have present and then absent, positive and then negative. R will automatically alphabetize. So if you want to specify a certain order, you can do it using this factor function in R. All right. Then we're going to check the dimension of our data, which is 2,000 patients, 1,000 patients with the disease, 1,000 patients without the disease. And we can look at the first 10 rows of the data. Remember that present with disease and a test result of positive. And if we did a summary of our data, we could check that out. And we would see that we have disease patients and the test result of those patients. All right. So we are going to let A be the positive test and B be the presence of the disease. And then we're going to talk about some specific definitions that were given in this chapter, which are prevalence, sensitivity, and specificity to start. So remember that prevalence is the proportion of the population that has the disease. So probability of B. Sensitivity is how good your test is at finding and testing positive given that you do have the disease, whereas specificity is the probability of not testing positive, so testing negative, specific to the group who does not have the disease. So your specificity is how specific are you in telling people they have a negative test when they don't have the disease, and how sensitive is your test is the probability of telling someone that they got a positive result given they do have the disease. So these three definitions are quite important, and we can find them in different ways. Remember that we could do a table of our disease status. And if we did that, that would tell you the number of people in each one. And if I did prop.table, that's going to give me the proportion of disease patients in this sample. And if I just want this first probability of presence, I can use the square bracket and just say, just give me the first element. So for the prevalence of the disease here, it should be 0.5, and we get 0.5. So then I can create a new table that has disease status versus the test result. And this matches what you see in the book. Present, absent, disease, we have 1,000 in each category. For positive tests, we have a total of 960, right? And here we can see present and a positive test, you have 950 people total. So what we could do here is say, let's look at just the one element of T. That should give us our 950 number that we're looking at on T, right? Because it's rows, comma, columns. So 1, 1 says the first row, the first column. So if I run that through, that's going to give me 950 just as I expected, right? And if we want, we can look at just the table of data $ disease. That's giving us how many people are present, right? So specific to the people who have the disease. So that first number should be 1,000, right? So we can also find sensitivity by doing the probability of A and B divided by the probability of B. That is our conditional formula. Okay, so we found the sensitivity. Now for specificity, we have the probability of not A given you're not in B. So using the conditional probability formula again, that's the probability of not A and not B divided by the probability of not B. Well, the probability of not A and not B, right? That's going to be that 990, right? That's the number of people who are not in A and not in B. And then the number of people who are not in B is also that 1,000, right? So we can calculate the specificity. So by doing that, we now have the sensitivity and specificity of the test. If we want to actually see what those numbers equaled out to be, then we need to type it out, right? And run that through. So our sensitivity in this case is 0.95 and our specificity is 0.99. So we do a better job telling people that they don't have the disease when they don't have it than telling people they do have the disease when they do have it. So sensitivity, the probability of testing positive given you have the disease. Specificity, the probability of testing negative given you do not have the disease. All right. Now, we could think of this in terms of the law of total probability, which we did in the last section, right? So the probability of A, and let's remind ourselves, right? A is a positive test, right? We know the probability of a positive test already, but we could think of this in terms of law of total probability just as an exercise. That's the probability of A given B times the probability of B plus the probability of A given not B times the probability of not B. And if we rearrange these formulas, we see that the first piece is just sensitivity, right? And multiply that by the prevalence, right? Now, probability of A given not B, that actually looks close to specificity, but not quite, right? Because specificity is the probability of not A given not B. But in this case, if we just do 1 minus specificity, we'll get there. And then the probability of not B, well, that's 1 minus the prevalence. So if we want, we can just double check. We know the probability of A in this case, right? We already have the test results. So the prop.table of our table of our test results, that will tell us the probability of A, right? So the probability of a positive test in this case is 0.48, right? The probability of a negative test, so the probability of not A, is 0.52. And what we can do is we can just double check to see if our formula is correct that we just made using the law of total probability, right? Sensitivity times prevalence plus 1 minus specificity times 1 minus prevalence. So we can calculate that as the probability of A. And when we do that, we got exactly what we thought we were going to get of 0.48. Now, this is a great exercise to do, and it just shows you how you can use many different measures to get to the same point. Obviously, you wouldn't need to use this long formula if you knew the test result, but sometimes people might not give you the probability of a positive test. They might just tell you, well, what's the sensitivity and the specificity? Recently, when I had my son and they were doing genetic testing, I went in and I asked them, what is the probability of a positive test result? And they wouldn't give me that information, but they would tell me the sensitivity and specificity and also the prevalence. So because I know my biostatistics, I was able to calculate what is the probability of a positive test in any given situation. Okay, we could do the same exact thing for the probability of not A, right? And first we say, okay, well, I know what the probability of not A is, right? That's the probability of not A given B times the probability of B plus the probability of not A given not B times the probability of not B, okay? And when I look at this closely, I recognize probability of B, that's prevalence, right? Probability of not B, well, that's 1 minus prevalence. This piece right here, probability of not A given not B, that's our specificity, right? And then the probability of not A given B, that's 1 minus our sensitivity. Make sure you work on these formulas and you understand how all of these relate together, because that's going to help you. All right, so we can once again calculate what was the probability of a positive test, what was the probability of a negative test, right? We already know the probability of A was 0.48 and the probability of not A is 0.52. All right, but just to double check that we did all of our formula calculations correctly, we run this again. The probability of not A is 1 minus the sensitivity times the prevalence plus the specificity times 1 minus the prevalence. Okay, so when we run that, we get 0.52, just as we predicted. All right, in equation 1.9 in our book, we talk about the positive predictive value and the negative predictive value. And the positive predictive value is the proportion of people among those responding positive who truly have the disease. So it's kind of the inverse of what we were doing before. What is the probability of testing positive given you have the disease, right? But now we're asking the reverse question for the positive predictive value, right? What's the probability of having the disease given you tested positive, right? Because in the real world, you don't know whether or not you have the disease, right? In the real world, you get a test result back that says you are pregnant, or you have COVID, or you have breast cancer, right? And you want to know, given that I just saw that, given I saw a positive result, right? What's the probability I actually have the disease? How stressed out should I be when I see this, right? So this is our positive predictive value. Okay, so we can just use Bayes' formula here and say, what does this end up being, right? Okay, when we do that, we can calculate this using the sensitivity, the prevalence, and the probability of A, right? So make sure you work out the math that you can get these formulas. But when we calculate this, we find out that the positive predictive value is 0.99. So that means the probability that you have the disease, given you saw a positive test, there's a 99% chance that you have the disease in this case. All right, that's pretty good. Now the negative predictive value, that is the proportion of people among those responding negative who truly do not have the disease, right? So your negative predictive value is asking the question, what is the probability that I don't have the disease given that I just got a negative test, right? And you can work out the math as we did here, and then you say, okay, well, this is really just a function of specificity, 1 minus the prevalence, and the probability of not A. So we can calculate the negative predictive value in this case. Okay, that's 0.95. All right, the last thing that we want to talk about is the odds form of the positive predictive value. All right, if we break this up, the odds form is PPV divided by 1 minus PPV, right? So this is an odds form of the positive predictive value. Okay, we can break this up into two pieces. The first piece is the likelihood ratio. And the second piece is the prevalence odds on the disease. So once again, this is odds because this is probability of B over 1 minus the probability of B. That's always an odds form type of thing. So here we have the prevalence odds on the disease times the likelihood ratio. All right, well, now that we have had everything saved, we can get the odds form of our positive predictive value is 95. Okay, And if we wanted to look at the likelihood ratio on itself, we get 95, and the prevalence odds here, right, was 1. So what does this mean? We can calculate this out just to prove that our formula is correct. Likelihood ratio times the prevalence odds, right? Still 95. How we interpret that is to say that a positive result is 95 times more likely to occur in a person with the disease than in one without the disease, right? Okay, so this is going over a lot of definitions, and you have to just get more and more comfortable creating new data sets, looking at what it is. But what have we really learned about definition-wise? We've learned negative predictive values, positive predictive values, odds form of the positive predictive value, the odds on the prevalence of the disease, a likelihood ratio, and sensitivity, specificity, prevalence. There's a lot of language that's going in here. So it takes a good amount of practice, but I know you guys can get this. So thank you for joining me in this video, and I look forward to seeing you next time.